Hello friends, we continue our discussion on the Leon-Diff's input-output model or input-output analysis. And today, we will be exploring how to solve an input-output flow table by using the matrix algebra method. Welcome to the session. Now we can explain how we can solve an input-output flow table or an input-output system, or what is known as the Leon-Diff's input-output model by using the matrices method or the method using the tool of matrices. From our last session, we have a balancing equation, right? We do have a equation like this: a11x1 plus a12x2 plus f1 equals x1, and the second equation was a21x1 plus a22x2 plus f2 equals x2. These were for a two-sector economy. We have two structural equations. We in fact reached this stage in our last session on the input-output analysis part 1. So this was the structural equation, and we will just convert this equation into a matrix form. Like we will form the matrices. We can have like x1 x2 equals a11 a12 a21 a22 into x1 x2 plus f1 f2. So we converted our equation or our structural equation into a matrix form where we have a vector of gross output. X1 is the total output of the first sector, X2 is the total output of the second sector. And we have a matrix here, a matrix of technological coefficient. We also already saw that A1, A11, A12, A21, A22, this is known as the technological coefficient or structural coefficient or the input-output coefficient, which was assumed to be fixed. As per the assumption of the model, these technological coefficients are assumed to be fixed because we are following a production function which is fixed proportion in nature. So we have a fixed proportion production function, and this input-output coefficient or structural coefficient or the technological coefficient are assumed to be fixed. And we have a vector of gross output plus F1 and F2, a vector of final demand or a final demand vector, which is F1 is the final demand for the first sector and F2 is the final demand for the second sector. So let us just transform this equation into like something like here. X equals Ax plus F, where X is nothing but the vector of gross output, A is nothing but the matrix which is a square matrix of technological coefficient. We have X again represent the vector of gross output, and F is the vector representing the final demand. Now let me just send this equation in like this. I will just make the Ax into the left hand side of the equation, and my equation will be like X minus Ax will be equal to F. We are using all these capital letters denote either a matrix or a vector. So since X is common, we can take X as a common item. So we will have an equation I minus A, which will be a matrix, into X will be equal to F, where I is the identity matrix of the same order. You already seen the identity matrix, right? So I minus A is the matrix of technological coefficient, into gross output will be equal to the final demand vector F. So we can solve for X. From this equation we can solve for X, and the value of X or the gross output will be equal to, we will send this I minus A into the right hand side of the equality sign. So it will be equal to I minus A inverse into F. So this will be our formula for solving an input-output table. So for solving an input-output table, we will obviously see how to solve an input-output flow table. We have this equation where X equals I minus A inverse into F. Here, this equation I minus A is known as the Leon-Diff matrix. So I minus A inverse into F. So we can calculate the gross output by using this equation. And next, we will see how we can use this equation, how we can use this matrix terminology to calculate the technological coefficient, to calculate the I minus A and find its inverse, and we will multiply it with F, and so that we can find out the value for the gross output. Let us explain by using a numerical example how to solve an input-output system by using a numerical example. Let us see how we can attempt a numerical example. Suppose we have a table like this, an input-output flow table. We have seen in as more or less a similar kind of a table in our last analysis as well, in our first session on input-output analysis. Similarly, we have two sectors here, an agriculture industry sector. The gross output of these sectors are divided into, or it is used as the input by the sector itself or some other sector, or it is used as for final demand. So out of the 1000 gross output of the first sector, which is agriculture sector, 300 is used by agriculture itself as input, 600 is used industry as its input, 100 is used for final demand. So 300, 600 plus 100 equals 1000. Similarly, the total output or the gross output of industrial sector is 2000, in which 400 is used by the agriculture sector as its input to agriculture here. 1200 is used by industry itself as its input, and 400 is used as for final demand. So 400 plus 1200 plus 400 equals 2000. So as per the assumption of the input-output model, the total output is either used as an input by some other sector or is used for final demand or for final consumption. We do have an assumption of input-output model. Now, given this flow table, we have a flow table here with all those identities and with all those balancing equations. Suppose that we are given a task to calculate the gross output to meet a new final demand. Let us say that we have a new final demand vector F equals, say, 200 and 800. So a new final demand vector or the two final demand value is given, which is F1 is equal to 200 and F2 is equal to 800, and we have a vector of final demand. Now let us suppose that we are given a task, a duty, to calculate the gross output so as to meet this new final demand. So this final demand changes to 200 and 800. Suppose that we are given a task to calculate a new gross output for the model when final demand changes from 100 to 200 and from 400 to 800. So how to calculate? For that, first we need to calculate the matrix for technological coefficient, the matrix A, right? So we have the matrix A, which is technological coefficient or input-output coefficient, which is obviously the first step in solving an input-output model. So for that purpose, let me just put 300 as this is nothing but x11, this is x12, and obviously this is f1. This is x21, this is x22, and this is f2. Now, first we need to calculate the value of A11. A11 is nothing but x11 by x1. So we multiply x11 with x1. This is our x1. This is our x1. this is our x1 and this is our x2. The output, the gross output of the first sector, the gross output of the second sector. So x11 by x1, that will be equal to say 300 by 1000. So value will be 0.3. 0.3. So similarly, I can calculate the value of A21. A21 is nothing but x21 by x1, which will be 400 by 1000, which will be equal to 0.4. So I have A11, I have A21. Now my task is, let me just put this somewhere here. F equals 200, 800. Right? So I need to calculate first A12. A12 will be equal to x12 by x2. x12 by x2. So I have 600 divided by 2000, which is nothing but 0.3 again. Now A22 will be equal to this one, x22. x22 divided by x2, which will be 1200 divided by 2000, which is equal to 0.6. So I have now the matrix for technological coefficient. Let me just put it like here. Let me just put the matrix of technological coefficient. A equals 0.3, 0.3, 0.4 as well as 0.6. So this is the matrix of technological coefficient, or what we call an input-output coefficient matrix, or a technological coefficient, or the structural coefficient matrix. So we have A. Now we have already calculated the A matrix, or the square matrix of a 2 by 2 order. Now the next step is we need to calculate, or we need to apply the formula to find out the gross output. And we already saw that the formula for calculating the final output F is X is equal to I minus A inverse into F. So this was the formula. This is the formula for calculating the gross output. I, which is an identity matrix, I minus A inverse into F. F is already given. We already had from the task itself, we already had the F. So our next task is to find I minus A and to find I minus A inverse. So for that, let me just calculate the I minus A. I minus A will be equal to, I means an identity matrix of the same order. So I have 1, 0, 0, 1 minus A. A is here. So I have 0.3, 0.3, 0.4 and 0.6. So I minus A will be equal to 1 minus 0.3 means I have 0.7. 0 minus 0.3 means minus 0.3. 0 minus 0.4 means minus 0.4. 1 minus 0.6 means 0.4. So I have the I minus A. Now we need to calculate the inverse of this particular matrix. So I have 0.7 minus 0.3 minus 0.4 and 0.4 here as the I minus A. Now, so the next task for us is to calculate the inverse. So let me just remove this equation. Yeah, let me just remove this equation from here. So already we had an F. So we just remove all these things of how to calculate the technological coefficient. So we have the I minus A. We have the I minus A. Our task will be to calculate the I minus A. So from our earlier session on the calculation of inverse, we know that I minus A inverse is nothing but the adjoint of I minus A divided by the determinant of I minus A. So first we need to calculate the determinant. Now let us first calculate the determinant. The determinant of I minus A will be equal to, so we will multiply the diagonal element minus the off diagonal elements. It will be equal to say 0.7 into 0.4 minus, within bracket, minus 0.4 into minus 0.3. So you will get 0.28 here and 0.12 there. So 0.28 minus 0.12, the answer will be 0.16. So we have the value for the determinant of I minus A, and we can solve. One checkpoint here. You can solve an input-output model provided I minus A should be a non-singular matrix. If you get a value as 0 here, you cannot simply solve an input-output table. So it should be a non-singular matrix. So non-singular matrix is those matrices we have already seen. Non-singular matrix is a square matrix for which the determinant is not equal to 0, and we got a 0.16 as value. So we do have a solution access. Now we can easily apply. So let me just remove all this here. F should be there, so that so I minus A is over. We have already calculated the determinant of I minus A. Now we need to calculate the adjoint of I minus A. For adjoint, first we need cofactors, right? So we should have the cofactors. So cofactors for the matrix, let me just put the I minus A once more. I minus A was equal to 0.7, minus 0.3, minus 0.4 and 0.4. This was our I minus A. So we need to calculate the adjoint matrix. So for that, first we need to calculate the cofactors. Cofactor of 0.7. Hope you remember how to calculate the cofactor, the adjoint and the inverse. We already had a video, and I will be putting the link of those video in our description box. And anybody who do have some confusion of how to calculate an inverse matrix, that means for solving we obviously need to have the I minus A inverse, right? So how to calculate an inverse matrix, we already made a video of that, and I will be putting the link of those video in our description box. See here. So the cofactor of 0.7 will be equal to minus 1 plus raised to 1 plus 1. So this gone, and what we have is 0.4. So value will be 0.4. Similarly, the cofactor of minus 0.3 is equal to minus 1 raised to the coefficient, which is 1 plus 2 into the minor, which is minus 0.4. Answer will be 0.4. Minus into minus, obviously you will get a plus. So you have a 0.4 there. So cofactor of minus 0.4 is equal to minus 1 raised to this row gone, this column gone, so I have minus 1 raised to 1 plus 2 into minus 0.3. Answer will be 0.3. Finally, the cofactor of 0.4 is equal to minus 1 raised to the position of 0. Which is 2 plus 2 into 0.7. Answer will be 0.7. So we have the matrix of cofactors. We have the matrix of cofactors, which is equal to 0.4. Again 0.4. The second row 0.3 and 0.7. So for adjoint, for the calculation of adjoint, we know that adjoint is the matrix of cofactors transpose. So adjoint of A equals Cij transpose. That means we will transform this or transpose this equation so that our final adjoint matrix will be equal to 0.4 here, 0.4 here. So finally we have 0.4 here. First row turned the first column and 0.3 in 0.7. So this will be our, so we have 0.4, 0.3, 0.4 as well as 0.7 as the adjoint matrix. So let me remove all these. Let me remove the calculation so that we can finally apply our formula, right? Let me just remove all these. So I do have the Ci. So now we can easily apply the I. So we already calculated the I minus A inverse. We have the adjoint here. We already had a determinant which was 0.16. So now we can calculate the equation. We have the formula x is equal to I minus A inverse into F, where I minus A inverse into adjoint of I minus A divided by determinant of I minus A into F. So adjoint we already had here like 0.4, 0.3, 0.4 and 0.7. This is the adjoint divided by the determinant. We already had the determinant which is 0.16 into, so this part is over. This part we already calculated the I minus A inverse into F. F is nothing but F is the vector of final demand and our vector is 200 and 800. So now we need to simply solve this equation by using the matrix multiplication method. So x will be equal to, how to multiply the matrix with a vector? Multiply each element of the row with column and do not forget to divide it with 0.16. So answer will be 0.4 into 200. We just put a bracket here plus 0.3 into 800 whole divided by 0.16 because 0. Should be divided by the determinant. Similarly, you have second row which is 0.4 into 200 plus 0.7 into 800 whole divided by 0.16. Once you solve this equation, you will get value as 2000 for this particular solution and 4000 for the second solution. So the final solution or the final vector which is x will be equal to 2000 and 4000. So this is the gross output. 2000 for the gross output of the first sector which is our agriculture sector and 4000 is the gross output of industrial sector to meet the final demand vector which is 200 and 800. So this is how we solve an input-output flow table, an input-output matrix or a Leon-Diff input-output table by using the formula, by using the method of matrices, by using the formula where gross output equals I minus A, which is Leon-Diff matrix, I minus A inverse into F. So for the calculation of I minus A inverse, we need to have the adjoint of I minus A along with the determinant of I minus A, and the solution of input-output possible only when the I minus A, which is the Leon-Diff matrix, should be non-singular. That means determinant should not be equal to 0. This is how we solve an input-output flow table. Hope that this session, the final session on input-output analysis is useful to you. We will continue our discussion on the mathematical tools in the coming session as well. Thank you for your company. So until we meet next time, stay safe, happy learning. Thank you.